A metal ion in aqueous solution is a cation, dissolved in water, of chemical formula, M, H2O, N, Z+. The solvation number, N, determined by a variety of experimental methods is 4 for Li and Be2 and 6 for elements in periods 3 and 4 of the periodic table. Lanthanide and actinide aqua ions have solvation number of 8 and 9. The strength of the bonds between the metal ion and water molecules in the primary solvation shell increases with the electrical charge, Z, on the metal ion and decreases as its radius, R, increases. Aqua ions are subject to hydrolyses. The logarithm of the first hydrolysis constant is proportional to Z2 per ranking for most aqua ions. The aqua ion is associated, through hydrogen bonding with other water molecules in a secondary solvation shell. Water molecules in the first hydration shell exchange with molecules in the second solvation shell and molecules in the bulk liquid. The residence time of a molecule in the first shell varies among the chemical elements from about 100 picoseconds to more than 200 years. Aqua ions are prominent in electrochemistry. Introduction to metal aqua ions. Most chemical elements are metallic and form simple aqua ions with a formula, M, H2O, N, Z+ when the oxidation state is 1, 2 or 3. With the higher oxidation states the simple aqua ions dissociate, losing hydrogen ions to yield complexes that contain both water molecules and hydroxide or oxide ions, such as the vanadium, 4, species, VO, H2O, 5, 2+. In the highest oxidation state only oxyanions, such as the permanganate, 7, ion, MnOA, 4 are known. In aqueous solution the water molecules directly attached to the metal ion are said to belong to the first coordination sphere, also known as the first, or primary, solvation shell. The bond between a water molecule and the metal ion is a dative covalent bond, with the oxygen atom donating both electrons to the bond. Each coordinated water molecule may be attached by hydrogen bonds to other water molecules. The latter are said to reside in the second coordination sphere. The second coordination sphere is not a well-defined entity for ions with charge 1 or 2. In dilute solutions it merges into the water structure in which there is an irregular network of hydrogen bonds between water molecules. With tripositive ions the high charge on the cation polarizes the water molecules in the first solvation shell to such an extent that they form strong enough hydrogen bonds with molecules in the second shell to form a more stable entity. The strength of the metal-oxygen bond can be estimated in various ways. The hydration enthalpy, though based indirectly on experimental measurements, is the most reliable measure. The scale of values is based on an arbitrarily chosen 0, but this does not affect differences between the values for two metals. Other measures include the MO vibration frequency and the MO bond length. The strength of the MO bond tends to increase with the charge and decrease as the size of the metal ion increases. In fact, there is a very good linear correlation between hydration enthalpy and the ratio of charge squared to ionic radius, Z2 per ranking. For ions in solution, Shannon's effective ionic radius is the measure most often used. Water molecules in the first and second solvation shells can exchange places. The rate of exchange varies enormously, depending on the metal and its oxidation state. Metal aqua ions are always accompanied in solution by solvated anions, but much less is known about anion solvation than about cation solvation. Understanding of the nature of aqua ions is helped by having information on the nature of solvated cations in mixed solvents and non-aqueous solvents, such as liquid ammonia, methanol, dimethylformamide and dimethyl sulfoxide to mention a few. Occurrence in nature, aqua ions are present in most natural waters. Na+, K+, Mg2+, and Ca2+ are major constituents of seawater. Many other aqua ions are present in seawater in concentrations ranging from ppm to ppt. The concentrations of sodium, potassium, magnesium and calcium in blood are similar to those of seawater. Blood also has lower concentrations of essential elements such as iron and zinc. Sports drink is designed to be isotonic and also contains the minerals which are lost in perspiration. magnesium and calcium ions are common constituents of domestic water and are responsible for permanent and temporary hardness, respectively. They are often found in mineral water. Experimental methods. Information obtained on the nature of ions in solution varies with the nature of the experimental method used. Some methods reveal properties of the cation directly, others reveal properties that depend on both cation and anion. Some methods supply information of a static nature, a kind of snapshot of average properties, others give information about the dynamics of the solution. Nuclear magnetic resonance ions for which the water exchange rate is slow on the nmr timescale give separate peaks for molecules in the first solvation shell and for other water molecules. The solvation number is obtained as a ratio of peak areas. Here it refers to the number of water molecules in the first solvation shell. Molecules in the second solvation shell exchange rapidly with solvent molecules, giving rise to a small change in the chemical shift value of uncoordinated water molecules from that of water itself. The main disadvantage of this method is that it requires fairly concentrated solutions, with the associated risk of ion pair formation with the anion. X-ray diffraction A solution containing an aqua ion does not have the long-range order that would be present in a crystal containing the same ion, but there is short-range order. X-ray diffraction on solutions yields a radial distribution function from which the coordination number of the metal ion and metal oxygen distance may be derived. With aqua ions of high charge, some information is obtained about the second solvation shell. This technique requires the use of relatively concentrated solutions. X-rays are scattered by electrons, so scattering power increases with atomic number. This makes hydrogen atoms all but invisible to X-ray scattering. Large-angle X-ray scattering has been used to characterize the second solvation shell with trivalent ions such as CO3+ and RH3+. The second hydration shell of CO3+ was found to have 7001130000000 unregistered trademark 13A ±1 molecules at an average distance of 6990402000000 unregistered trademark 402A ±20 pm. This implies that every molecule in the first hydration shell is hydrogen bonded to two molecules in the second shell. Neutron diffraction diffraction by neutrons also give a radial distribution function. In contrast to X-ray diffraction, neutrons are scattered by nuclei and there is no relationship with atomic number. Indeed, use can be made of the fact that different isotopes of the same element can have widely different scattering powers. In a classic experiment, measurements were made on 4 nickel chloride solutions using the combinations of 58 Ni, 60 Ni, 35 centiliters and 37 centiliters isotopes to yield a very detailed picture of cation and anion solvation. Data for a number of metal salts show some dependence on the salt concentration. A. Moles solute per kg of solvent. Angle between MO and the HM lines, M equals midpoint between H or D atoms. Figures in brackets are standard deviations on the last significant figure of the value. Most of these data refer to concentrated solutions in which there are very few water molecules that are not in the primary hydration spheres of the cation or anion, which may account for some of the variation of solvation number with concentration even if there is no contact ion pairing. The angle I gives the angle of tilt of the water molecules relative to a plane in the aqua ion. This angle is affected by the hydrogen bonds formed between water molecules in the primary and secondary solvation shells. The measured solvation number is a time-averaged value for the solution as a whole. When a measured primary solvation number is fractional, there are two or more species with integral solvation numbers present in equilibrium with each other. This also applies to solvation numbers that are integral numbers, within experimental error. For example, the solvation number of 5.5 for a lithium chloride solution could be interpreted as being due to presence of two different aqua ions with equal concentrations. Li, H2O, 6, plus, Li, H2O, 5, plus H2O. Another possibility is that there is interaction between a solvated cation and an anion, forming an ion pair. This is particularly relevant when measurements are made on concentrated salt solutions. For example, a solvation number of 3 for a lithium chloride solution could be interpreted as being due to the equilibrium, Li, H2O, 4, plus clap, Li, H2O, 3 centiliters plus H2O, lying wholly in favor of the ion pair. Vibrational spectra equals, infrared spectra and Raman spectra can be used to measure the MO stretching frequency in metal aqua ions. Raman spectroscopy is particularly useful because the Raman spectrum of water is weak whereas the infrared spectrum of water is intense. Interpretation of the vibration frequencies is somewhat complicated by the presence, in octahedral and tetrahedral ions, of 2 vibrations, a symmetric one measured in the Raman spectrum and an anti-symmetric one, measured in the infrared spectrum. Although the relationship between vibration frequency and force constant is not simple, the general conclusion that can be taken from these data is that the strength of the MO bond increases with increasing ionic charge and decreasing ionic size. The MO stretching frequency of an aqua ion in solution may be compared with its counterpart in a crystal of known structure. If the frequencies are very similar, it can be concluded that the coordination number of the metal ion is the same in solution as it is in a compound in the solid state. Dynamic methods data such as conductivity, mobility and diffusion relate to the movement of ions through a solution. When an ion moves through a solution, it tends to take both first and second solvation shells with it. Hence solvation numbers measured from dynamic properties tend to be much higher than those obtained from static properties. Solvation numbers and structures. Alkali metals solvation numbers of 3 to 6 have been found for lithium aqua ions. Solvation numbers less than 4 may be the result of the formation of contact ion pairs. The higher solvation numbers may be interpreted in terms of water molecules that approach, Li, H2O, 4, plus through a face of the tetrahedron, though molecular dynamic simulations may indicate the existence of an octahedral aqua ion. There are most probably 6 water molecules in the primary solvation sphere of the sodium ion. For potassium, rubidium and cesium, even the primary solvation shell is not well defined. Alkaline earth metals B, H2O, 4, 2 plus has a very well-defined primary solvation shell. The BO4 part has tetrahedral symmetry, Td. Mg, H2O, 6, 2 plus is also a well-characterized species, with an octahedral core. The situation for calcium is more complicated. Neutron diffraction data gave a solvation number for calcium chloride, CaCl2, which is strongly dependent on concentration, 700110000000000 unregistered trademark 10.0 A plus or minus 0.6 at 1 Molybdenum 3, decreasing to 7006400000000 unregistered trademark 6.4 A plus or minus 0.3 at 2.8 Molybdenum 3. The Shannon radius of the 6-coordinate calcium ion is 100 pm compared to 72 pm for magnesium, a 28% increase in size. This allows for higher equation numbers, and the lower charge density results in weaker MO bonds, which makes ion pairing easier. Various solid hydrates are known with 8 coordination in square antiprism and dodecahedral geometry. Aluminium and group 3 metals by convention aluminium is placed in group 13, with gallium, indium and thallium. Nevertheless, a comparison of aluminium and scandium aqua ions illustrates a trend between the congeners Na+/K+, Mg2+/Ca2+, and Al3+/Sc3+, which depends on the increase in size ongoing from rows 3 to 4 in the periodic table. Shannon radii for 6-coordinate Al3+ and Sc3+ are 54 and 74.5 pm. Ga3+ has a Shannon radius of 62 pm, only about 13% larger than that of Al3+. This is due to the presence of the 10 elements between scandium and gallium, which make an additional contribution to the general decrease in size across all rows of the periodic table. The aluminium aqua ion, Al, H2O, 6, 3+ is very well characterized in solution and the solid state. The Al O6 core has octahedral symmetry, point group O. there is now a substantial body of indirect evidence that 7 molecules of water are present in the aqua ion of scandium, Sc3+. Yttrium, 3, has approximately the same Shannon radius as holmium, 3, so Y3+ has very similar properties to those of Ho3+, so its aqua ion is probably 8 coordinate. The lanthanum aqua ion is probably 9 coordinate, as are those of the lighter lanthanides. Transition metals and group 12 metals equals. The ions of these metals in the +2 and +3 oxidation states have a solvation number of 6. All have a regular octahedral structure except the aqua ions of chromium, 2, and copper, 2, which are subject to Jahn-Teller distortion. In the copper case the two axial KO distances are 238 pm, whereas the four equatorial KO distances are 195 pm. Silver, I, is probably 4 coordinate, Ag, H2O, 4, plus. A solvation number of 6 with an octahedral structure is well established for zinc, 2, and cadmium, 2, in dilute solutions. In concentrated solutions the Zn2+ ion may adopt a 4-coordinate, tetrahedral, structure, but the evidence is not conclusive because of the possibility of ion pairing and/or hydrolyses. The solvation number of mercury, 2, is most likely to be 6. The bis-aqueous structure of the mercury, I, ion, H2O, HgHg, OH2, found in solid compounds, is also found in solution. Another aqua species in which there is a metal-metal bond is the molybdenum, 2, species formulated as H4O, MoMo, OH4, 4+ on the basis of theoretical considerations of the nature of the MoMo bond. Each molybdenum is surrounded by 4 water molecules in a square planar arrangement, in a structure similar to that of the known structure of the chloro complex, Mo2Cl8, 4A. The presence of a 5th water molecule in the axial position is not ruled out, however. There are a few divalent and trivalent aqua ions of transition metals in the 2nd and 3rd transition series. With oxidation state 4, however, only hydrolyzed species exist. Group 13 to 15 metals equals, the aqua ions of gallium, 3, and indium, 3, and thallium, 3, have a solvation number of 6. The aqua ion of thallium, I, is often assumed to be 6 coordinate, but this assumption is not based on strong experimental evidence. The Shannon radius of Tl+, at 150 pm, is not very different from that of K+, at 138 pm, so some similarity between Tl+ and K+ chemistry is both expected and observed. The solvation number of the tin, 2, aqua ion, Sn, H2O, N, 2+ is not known with any certainty due to the presence of hydrolysis in the concentrated solutions needed for X-ray scattering measurements. The same is true for the lead, 2, aqua ion. With bismuth, 3, there is indirect evidence for a solvation number of 9. A non-norhydrate has been characterized in the solid state, with a face-cap trigonal prism structure. The Shannon radius for 9-coordinate bismuth is comparable to that of neodymium, for which a solvation number of 9 is well established. Lanthanides and actinides equals. The trivalent lanthanide ions decrease steadily in size from lanthanum to lutetium, an effect known as the Lanthanide Contraction. Nevertheless, there is strong evidence that the hydration number changes from 9 to 8 at around gadolinium. Structures of aqua ions in the solid state include the 9-coordinate tricap trigonal prism structure with the lighter lanthanide ions and the 8-coordinate square antiprism structure with the heavier lanthanide ions. There are no experimental data for the solvation state of cerium, 4, or europium, 2. Solvation numbers of 9 or more are believed to apply to the actinide ions in the +3 and +4 oxidation states, but an experimental value is available only for thorium, 4. Oxo-aqua-cations equals, some elements and oxidation states higher than 3 form stable, equated, oxo-ions. Well-known examples are the vanadilyl, 4, and uranyl, 6, ions. They can be viewed as particularly stable hydrolysis products in a hypothetical reaction such as B, H2O, 6, 4 plus a, VO, H2O, 5, 2 plus 2 hours plus, the vanadium has a distorted octahedral environment of 1 oxide ion and 5 water molecules. Vanadium, V, is believed to exist as the dioxo ion, VO2, H2O, 4, plus at pH less than 2, but the evidence for this ion depends on the formation of complexes, such as oxalate complexes which have been shown to have the VO plus, 2 unit, with Psi-VO bonds, in the solid state. The chromium, 4, ion, CrO, H2O, 5, 2 plus, similar to the vanadium ion has been proposed on the basis of indirect evidence. The uranyl ion, UO2+, 2, has a trans structure. The aqua ion UO2+, 2, AC, has been assumed, on the basis of indirect evidence, to have 5 water molecules in the plane perpendicular to the OUO axis in a pentagonal bipyramid structure, point group D5H. However, it is also possible that there are 6 water molecules in the equatorial plane, hexagonal bipyramid, point group D6H, as many complexes with this structure are known. The solvation state of the plutonyl ion, PuO2+, 2, is not known. Thermodynamics. The main goal of thermodynamics in this context is to derive estimates of single-ion thermodynamic quantities such as hydration enthalpy and hydration entropy. These quantities relate to the reaction, Mz plus solvent Mz+. The enthalpy for this reaction is not directly measurable, because all measurements use salt solutions that contain both cation and anion. Most experimental measurements relate to the heat evolved when a salt dissolves in water, which gives the sum of cation and anion solvation enthalpies. Then, by considering the data for different anions with the same cation and different cations with the same anion, single-ion values relative to an arbitrary zero, are derived. Other values include Zn2 plus minus 2044.3, CD2 plus minus 1805.8 and Ag plus minus 475.3 kilojoules molar 1. There is an excellent linear correlation between hydration enthalpy and the ratio of charge squared, Z2, to MO distance, ref. IH equals 69,500 Z2/ref. Values for transition metals are affected by crystal field stabilization. The general trend is shown by the magenta line which passes through Ca2+, Mn2+, and Zn2+, for which there is no stabilization in an octahedral crystal field. Hydration energy increases as size decreases. Crystal field splitting confers extra stability on the aqua ion. The maximum crystal field stabilization energy occurs at Ni2+. The agreement of the hydration enthalpies with predictions provided one basis for the general acceptance of crystal field theory. The hydration enthalpies of the trivalent lanthanide ions show an increasingly negative values at atomic number increases, in line with the decrease in ionic radius known as the Lanthanide contraction. Single-ion hydration entropy can be derived. Values are shown in the following table. The more negative the value, the more there is ordering in forming the aqua ion. It is notable that the heavy alkali metals have rather small entropy values, which suggests that both the first and second solvation shells are somewhat indistinct. Hydrolysis of aqua ions. There are 2 ways of looking at an equilibrium involving hydrolysis of an aqua ion. Considering the dissociation equilibrium, M, H2O, N, Z plus H plus, M, H2O, N1, OH, Z1, plus, the activity of the hydrolysis product, emitting the water molecules, is given by. The alternative is to write the equilibrium as a complexation or substitution reaction, M, H2O, N, Z plus OA, M, H2O, N1, OH, Z1, plus H2O, in which case the concentration of hydrogen and hydroxide ions are related by the self-ionization of water, Kw equals H plus OA, so the 2 equilibrium constants are related as. In practice, the first definition is more useful because equilibrium constants are determined from measurements of hydrogen ion concentrations. In general, charges are omitted for the sake of generality and activities have been replaced by concentrations. are cumulative hydrolysis constants. Modeling the hydrolysis reactions that occur in solution is usually based on the determination of equilibrium constants from potentiometric titration data. The process is far from straightforward for a variety of reasons. Sometimes the species in solution can be precipitated as salts and their structure confirmed by X-ray crystallography. In other cases, precipitated salts bear no relation to what is postulated to be in solution, because a particular crystalline substances may have both low solubility and very low concentration in the solutions. First hydrolysis constant equals the logarithm of hydrolysis constant, K1, minus 1, for the removal of one proton from an aqua ion, M, H2O, N, Z plus H plus, M, H2O, N1, OH, Z1, plus, M, OH, Z1, plus equals K1, minus 1, MZ plus, H plus A1, shows a linear relationship with the ratio of charge to MO distance, ZD. Ions fall into four groups. The slope of the straight line is the same for all groups, but the intercept, A, is different. The cations most resistant to hydrolysis for their size and charge are hard pre-transition metal ions or lanthanide ions. The slightly less resistant group includes the transition metal ions. The third group contains mostly soft ions of post-transition metals. The ions which show the strongest tendency to hydrolyze for their charge and size are Pd2+, Sn2+, and Hg2+. The standard enthalpy change for the first hydrolysis step is generally not very different from that of the dissociation of pure water. Consequently, the standard enthalpy change for the substitution reaction, M, H2O, N, Z++ OA, M, H2O, N1, OH, Z1, plus H2O, is close to zero. This is typical of reactions between a hard cation and a hard anion, such as the hydroxide ion. It means that the standard entropy charge is the major contributor to the standard free energy change and hence the equilibrium constant. Ig equals RTLNK equals IH, Ts. The change in ionic charge is responsible for the effect as the aqua ion has a greater ordering effect on the solution than the less highly charged hydroxo complex. Multiple hydrolysis reactions equals. The hydrolysis of beryllium shows many of the characteristics typical of multiple hydrolysis reactions. The concentrations of various species, including polynuclear species with bridging hydroxide ions, change as a function of pH up to the precipitation of an insoluble hydroxide. Beryllium hydrolysis is unusual in that the concentration of B, H2O, 3, OH, plus is too low to be measured. Instead a trimmer 6, OH33+ is formed, whose structure has been confirmed in solid salts. The formation of polynuclear species is driven by the reduction in charge density within the molecule as a whole. The local environment of the beryllium ions approximates to B, H2O, 2, OH, 2, plus. The reduction in effective charge releases free energy in the form of a decrease of the entropy of ordering of the charge centers. The hydrolysis product of aluminium formulated as Al13O4, OH, 24, H2O, 12, 7 plus is very well characterized and may be present in nature in water at pH circa 5.4. The overall reaction for the loss of two protons from an aqua ion can be written as M, H2O, N, Z plus 2 hours plus, M, H2O, N2, OH, 2, Z2, plus. However, the equilibrium constant for the loss of two protons applies equally well to the equilibrium, M, H2O, N, Z plus 2 hours plus, MO, H2O, N2, Z2, plus H2O, because the concentration of water is assumed to be constant. This applies in general. Any equilibrium constant is equally valid for a product with an oxide ion as for the product with two hydroxyl ions. The two possibilities can only be distinguished by determining the structure of a salt in the solid state. Oxo bridges tend to occur when the metal oxidation state is high. An example is provided by the molybdenum 4 complex, Mo3O4, H2O, 9, 4+, in which there is a triangle of molybdenum atoms joined by I-fluorine bonds with an oxide bridge on each edge of the triangle and a fourth oxide which bridges to all three Mo atoms. Oxyanions . There are very few oxo-aqua ions of metals in the oxidation state +5 or higher. Rather, the species found in aqueous solution are monomeric polymeric oxyanions. Oxyanions can be viewed as the end products of hydrolysis, in which there are no water molecules attached to the metal, only oxide ions. Exchange kinetics: a water molecule in the first solvation shell of an aqua ion may exchange places with a water molecule in the bulk solvent. It is usually assumed that the rate-determining step is a dissociation reaction. H2O, N, Z plus A, H2O, N1, Z plus H2O, the symbol signifies that this is the transition state in a chemical reaction. The rate of this reaction is proportional to the concentration of the aqua ion, A. The proportionality constant, K, is called a first-order rate constant at temperature T. The unit of the rate constant for water exchange is usually taken as Moldma3 The half-life for this reaction is equal to log 2 per carat. This measure is useful because it is independent of concentration. It has the dimension of time. The quantity 1 per carat, equal to the half-life divided by 0.6932, is known as the residence time or time constant. The residence time for water exchange varies from about 10^10s for CS+ to about 10+10s for A3+. It depends on factors such as the size and charge on the ion and, in the case of transition metal ions, crystal field effects. Very fast and very slow reactions are difficult to study. The most information on the kinetics of water exchange comes from systems with a residence time between about 1I1/4s and 1s. The enthalpy and entropy of activation, I_{Euro} and I_{Euro} can be obtained by observing the variation of rate constant with temperature. The kinetic parameters for aqua ions of the transition metals are affected by crystal field stabilization energy on both the aqua ion and its dissociation product, which has one less water molecule in the primary solvation shell. This explains the inertness of Cr3+, which has an octahedral structure and a d3 electronic configuration, and RH3+ and A3+, which are also octahedral and have a low spin d6 configuration. Trivalent ions have longer residence time than divalent ions, except for the very large lanthanide ions. The values in the table show that this is due to both activation enthalpy and entropy factors. Mechanisms. The assignment of mechanisms to the water exchange reaction has not yet been made unambiguously. The simple dissociation mechanism needs to be modified to take into account the presence of a second solvation shell. In all cases, exchange between molecules in the second shell in bulk water is fast compared to the rate-determining step. 3 possible mechanisms arise. IT mechanism. A water molecule leaves the first solvation shell and enters the second shell. IA mechanism. The same exchange reaction takes place, but there is a significant interaction, in the transition state, between the incoming water molecule and the metal ion. A mechanism. This is an associative mechanism involving a molecule from the bulk solvent. This classification represents extreme cases. The actual mechanism may have something of an intermediate nature. The most useful parameter for distinguishing between possible mechanism is the activation volume change, I_Euro, which is obtained from the pressure variation of the rate constant. The activation volume increases for dissociative mechanisms and decreases for associative mechanisms. Formation of complexes. Metal aqua ions are often involved in the formation of complexes. The reaction may be written as PMX plus AC plus QLIR, MPLQ, PXQY plus. In reality, this is a substitution reaction in which one or more water molecules from the first hydration shell of the metal ion are replaced by ligands, L. The complex is described as an inner sphere complex. A complex such as ML, PQ, plus may be described as a contact ion pair. When the water molecule, S, of the second hydration shell are replaced by ligands, the complex is said to be an outer sphere complex, or solvent shared ion pair. The formation of solvent shared or contact ion pairs is particularly relevant to the determination of solvation numbers of aqua ions by methods that require the use of concentrated solutions of salts, as ion pairing is concentration dependent. Consider, for example, the formation of the complex MgCl+ in solutions of MgCl2. The formation constant, K, of the complex is about 1 but varies with ionic strength. The concentration of the rather weak complex increases from about 0.1% for a 10 mm solution to about 70% for a 1 m solution. Electrochemistry. The standard electrode potential for the half-cell equilibrium Mz++Za shear M(s) has been measured for all metals except for the heaviest trans-uranium elements. As the standard electrode potential is more negative, the aqua ion is more difficult to reduce. For example, comparing the potentials for zinc with those of iron -0.47 V, Fe3, -0.06 V, it is seen that iron ions are more easily reduced than zinc ions. This is the basis for using zinc to provide anodic protection for large structures made of iron or to protect small structures by galvanization. References. Bibliography, Baez, compare. Mesmer, R.E., 1976. The Hydrolysis of Cations. Malabar, Florida, Robert E. Krieger. ISBN 0-89974-892-5. Burgess, John. Metal Ions in Solution. Chichester, Ellis Harwood. ISBN 0-85312-027-7. Richens, David. The Chemistry of Aqua Ions. Wiley. ISBN 0-471-97058-1. Sturm, Werner. Morgan, James J. Aquatic Chemistry, Chemical Equilibria and Rates in Natural Waters. Wiley-Blackwell. ISBN 0-471-51185-4. Schweitzer, George K. Pesterfield, Lester L. The Aqueous Chemistry of the Elements. Oxford, OUP. ISBN 0-19-539335-X.